Good morning, everybody. Hopefully, yes, good. It looks like you can hear me. We are wrapping up Unit 2 this week. We have 2 more lectures this week, one today and then one again on Wednesday, after which on Friday will be our second exam. As I mentioned, a couple of minor changes for the second exam, notably each problem will hopefully be a little bit shorter, just a little bit, and as a result there will be a sort of additional problem sort of built in, so the exam should be roughly the same as it was before. Just keep in mind that the first half of problems are designed to be very straightforward. So if you're spending 20, 30 minutes on the first step of a problem, you're probably overthinking it. The other thing I want to mention is that I did finally send out the first round of official academic integrity violation notifications. I am in the process of filing those. There's going to be a second round of warnings sent out today. They are warnings because they are a slightly different type of infraction, and out of an abundance of caution, I'm concerned that I may have swept up a few innocent parties in my investigation. And so just to be very, very sure I'm not negatively impacting any innocent folks' academic record, this round of emails that's going to go out today and tomorrow are very much just warnings. No formal report will be submitted this time around, but it's worth noting that if the practice repeats again, that will no longer be the case. So, you know, consider this email if you are one of the let's say, folks that engaged in these activities, if you are one of them, consider this your first and only warning. And if you are getting this email by mistake, if you are one of the very small handful of people who may have been tied up in this innocently, just make sure you stay doing what you're doing. That's all. And you may want to distance yourselves from the associated content that I'm going to be reaching out to. Other than that, it is my sincere hope that Exam 2 will not be riddled with the same amount of academic integrity issues. It is specifically the 3 that I sent out on Friday that were the most severe, and I fully expect that if it happens again, I will be equally severe. I'd like to remind everybody that I'm being pretty lenient with what we're allowing on the exams, open notes, you know, all of that kind of stuff. My only real hard and fast rule is that you not share solutions, or more importantly, outsource solutions to, say, websites like Chegg. That violation in particular is met with very severe consequences. And I, just as a general warning, I hate to be all doom and gloom, but will remind you that formal academic integrity violations can result in expulsion. Not just a slap on the wrist, although that is possible. They can end with them saying you are no longer allowed to be a student here. So weigh very carefully what your desired outcome is and whether your entire career is worth the risk of engaging with one of these external websites. All right, enough doom and gloom. Let's get back to the exciting stuff of circuit theory. I know, that's really exciting, right? We're all super happy to be here at 9 o'clock in the morning, for those of you who are live in the chat, talking about Physics 2 and circuits. Hooray. Today we are covering basically 2 things. We're going to talk really quickly about how to do equivalent resistor circuits. It's going to turn out that those are really similar to equivalent capacitance circuits, so we're not going to spend a lot of time on it. What we are going to spend a lot of time on are the advanced circuit analysis rules, which are specifically referred to as Kirchhoff's laws, and that is going to be relevant for homework 7 for those of you who are kind of looking ahead. After we talk about Kirchhoff's laws today, we'll wrap up Unit 2 by talking about resistor and capacitor circuits on Wednesday, and then we'll be ready to go for the exam. So without any further ado, I would like to pause here and just briefly summarize some symbols that we use in circuit diagrams. Now, most of these you will not see in this course, so well, many of these. For example, we're never really going to practically work with diodes or transistors, so although I want you to know what symbols we use in case you see them, these we're not really going to be doing too much with. We also use these symbols, ammeter, a circle with an A in it and a circle with a V in it, to represent the devices we use to measure circuit properties. An ammeter is a device that is used to measure current. You connect it in series with whatever device you want to measure the current through. A circle with a V in it is a voltmeter. You connect it in parallel to whatever device you want to measure the voltage of. But really our bread and butter is going to be over here. And we've already seen, well, 3 of these. The EMF source, so that's something like a battery, the capacitor that we talked about at the beginning of Unit 2, and the resistor that we've been talking about the last couple of classes. In Unit 4, we're going to come back to this and we're going to introduce a new device called the inductor, but for now, that is not here. It's these 3 that we're going to be dealing with mostly here in Unit 2. Today we're focusing, however, mostly on resistors, and the first question we want to ask is, how do we connect multiple resistors together, and can we analyze that in a way like we did capacitors? The short answer is yes. In the same way that was the case for capacitors, where charge was the same in series and voltage was the same in parallel, we're going to see that current is the same in series devices. This makes sense because current is related to charge as a function of time. So if the charge is the same for circuit devices that are in series, then current should be as well. Similarly, we're going to see that voltage is still the same in parallel. Now, these 2 things allow us to define equivalent resistances in a very analogous way to how we defined equivalent capacitances. When you have current going through a set of resistors connected in series, though that current will remain the same, we can use Ohm's law to relate the voltage and the resistance, and we can calculate an equivalent resistance as just the sum. Why did that turn into an arrow? That seems like a really weird thing for it to do. As just the sum of the individual resistances. So when resistors are in series, they combine simply by adding. In a similar way, when we evaluate parallel connections, now it's the voltage that is the same, and we can relate the current to it through Ohm's law. And when we do that, we'll see that the resistances add inversely. I think a canny student out there who's paying close attention will notice that this seems very, very, very similar to capacitors. And that's because it is. There is just one small caveat. If we consider how series and parallel equivalent devices are calculated, and we compare capacitors, which is what we did before, where they add inversely for series and directly in parallel, resistors are simply the opposite. They add when they are in series, and they add inversely when they are in parallel. So all of the intuition that we developed for figuring out equivalent capacitance is going to serve us directly when we're trying to calculate equivalent resistance. We're just going to have to swap, and there's a typo right there. That should be R. We're just going to have to swap which one of these equations we do for each. As long as you can get a feel for that, then you're in good shape. Otherwise, the general algorithm, which is basically label all of the, label everything, combine things one step at a time by finding parallel and series connections, all that is going to be the same. Now, to that end, there are a couple of exercises here on the slides that include equivalent resistance calculations. Now, this one and this one are relatively straightforward, and I'm going to encourage that you go into the notes and work through those together, or like on your own, and just compare your results to what's in the notes. Because as much as I would love to spend a lot of time on this, we do have more complex topics to get to today. But I think for the purposes of this exercise, it is useful to go through at least one of these, and so I'm going to do so with this one, the most complicated version. Now you'll notice right off the bat, this is asking us for the equivalent resistance, all of the currents through each one of the resistors, all of the voltages across each one of the resistors, and the total power dissipated by the circuit. This is an excellent example of a complicated circuit that benefits from the approach where you just do it one step at a time, write out each step, labeling everything, and then working backwards. To see why, let us first label all of our voltages. And we're doing that with our little color coding that we did before. Remember that voltage is the same everywhere in a wire. But anytime you get to a circuit device, that voltage is going to change, meaning you have to label it a different color. In this case, that leads us to 4 different voltages throughout this circuit. Now, we want to identify things that are either in parallel or in series, and then combine them, do this one step at a time until we get our final result. Right away, if I look up here, I notice red to green across R1 is the same as red to green across R2. This indicates these resistors have the same voltage, and therefore we can combine them in parallel. When we do so, I'm going to just, let's see how quickly I can draw this. The end result, that is not what I wanted to do. No, dang it. Okay, try again. So what this is going to do is it's going to take my 2 resistors that are in parallel, that's R1 and looks like R2, as labeled, and we're going to combine those together in parallel. The other resistors are going to remain unaffected by this process, and so I'm just labeling their resistances, carrying them over from my original diagram. I am, however, going to have a new resistor here that is going to have a resistance of 1 over R equals 1 over 6 plus 1 over 12. So what I'm going to want to do is take the reciprocal of both sides. And so let's see, that's 2/12 plus 1/12. That gives us 3/12. Takes the inverse, that's 12 over 3, which is going to give us 4. Now I can go through and I do my labeling again, and it occurs to me I probably should have drawn the battery in here. That certainly hasn't gone anywhere. And I can, repeat the process and identify what's in series and what's in parallel. Just for completeness, note that the voltages may, and in fact may be, and in fact are different on these 2 sort of intermediate wires here. So red-green, red-purple, purple-blue, green-blue, none of those have the same voltage, so nothing's in parallel. However, it does seem pretty clear that these are in series and these are in series, so we can combine those as well. Now I'm going to redraw the circuit once again. This time just a little bit smaller. And what I end up with are new resistors, and maybe I'll do this in 2 different colors, that I get simply by adding these. So 4 plus 4 gives me 8. And 3 plus 5 also gives me 8, which means these are both 8 ohm resistors, and once again, I don't want to forget about the battery. And these were both made from series connections. It's probably obvious at this point that these last two resistors are connected in parallel. So I have one more step in my process. This is a parallel connection. And I'm just going to go ahead and get out of the way entirely as I draw my final equivalent circuit. Which is, of course, just a single equivalent resistance connected to a battery. Since those are in parallel, I get that as 1 over 8 plus 1 over 8. Then I take the reciprocal, and that is going to give me 4 ohms. And so that is my final answer for the equivalent resistance. It's worth noting at this point that I can actually also calculate the total power dissipated in the circuit. The reason being is I know that the battery is 12 volts, and I know that the total power is, well, it's really what it is I have to add up the power from all of these. But remember, the whole point of equivalent resistance or equivalent capacitance is that this circuit is indistinguishable from this one. So I can just calculate the power down here as well. Doing that is much more straightforward. I can just use one of my power equations. For example, I times V would be the base one. But that's not going to be useful to me because I don't know what I is yet. So instead, I'll use V squared divided by R. And that's just going to be 12 squared divided by R, which is 4, which will give me 36 watts. So by doing this process, I've solved the first and final part of the problem just straight off the bat, just by doing my circuit analysis. Now's the point where we start working backwards. We start with the most simple circuit, and we just note that the equivalent resistance has whatever voltage is across the battery. And that's just our starting point. Then we use Ohm's law, specifically either to calculate the current, which is voltage divided by resistance, or later to just get the voltage. And we can go back and forth between these. So in this case, we know the voltage and the resistance. We don't know the current. So we take the voltage, 12, divide it by 4 to get 3 amps. And that's the current. We then go backwards a step. Parallel circuits have the same voltage. So let me get out of the way again. So I take my voltage value from this circuit and I just translate it back to the other ones. And since I've chosen my colors poorly, let me just fix, yeah, there we go. So both of these resistors are at 12 volts. And so I can then calculate the current using V divided by R. 12 divided by 8 is 1.5 amps. Note that these two currents add up to this one. Now I work backwards. Series connections have the same current. So all of these have the same 1.5 amps running through them. I just took the values from here, and since series connections have the same current, I just wrote those backwards. I can then get the voltage by multiplying the current times the resistance, 1.5 times 4 gives me 6 volts in both of these cases, whereas 1.5 times 3 gives me 4.5, and what's that going to be? 5, 2.5, 7.5. Finally, my last step is that parallel connections have the same voltage, which means both of these have 6 volts, which when I apply Ohm's law gives me 1 amp and 0.5 amps. Now if I just come back and first I'm going to get rid of these messy colors so everything's labeled clearly. If I just read everything else off the diagram, these are all just voltages that I've already calculated. Then I have my entire answer to part B, and it was always just a simple application of Ohm's law. And that's all there is to circuits like this, regardless of their complexity. All there is to it, whatever that means. A couple of things I'll note. It would be tempting to say that the voltage and current always splits evenly, but we'll note that that's not the case. For example, here, we have the current that has different values in each parallel branch. And here we have voltages that are different in each parallel branch. There's a question in the chat. Can I explain again why the resistance and capacitance have different formulas like I've shown before? The short answer is no. I do not have time to go through all of that. I fully do recommend that you go through the notes for a more nuanced discussion of this. But I can give you the answer in broad strokes. And it basically just boils down to how voltage and current is related to one another and which rule that we're using to relate them. It basically boils down to the following difference. For capacitance, C was equal to Q divided by V. But Ohm's law, keep trying to draw a double-headed arrow. There we go. But Ohm's law, when I solve it for current, gives me, solve it for resistance, gives me V divided by I. So the basic idea is, note that here, the thing that depends on charge, let me put it this way. Here, voltage is on the top. Here, voltage is on the bottom. And the thing that depends on charge is swapped. So because these fundamental relationships kind of have inverse dependence on voltage, that leads to the outcome, that leads to the sort of fundamental behavior being inverted for the two of them. It is otherwise exactly the same argument that we went through for the capacitor back in like 2 or 3 lectures ago. But the fact that their underlying fundamental equations have an inverse dependence on voltage leads to the fact that these results are inverted. Excellent question. Sorry I can't go into it more. Okay, so like I said, there are 2 more examples here that I strongly encourage you to analyze on your own. But we're going to spend the rest of today's lecture on Kirchhoff's rules. Now, the good news is that we've actually already done one of these. Last class, when we were going through those complicated resistor circuits, we did this process of labeling polarities and summing up voltages around a loop. That is called the loop rule, and that's the first half of what we're talking about today. So you're already well equipped to get started on the advanced circuit analysis we're doing from here on out. The other thing that we need to do, include in this, is the so-called junction rule. This says at any junction in a circuit, and at this point I want to pause and just indicate that a junction is a place where 3 or more wires come together. So, for example, a very simple junction might look like this. Or a very complicated junction might look like this. You know, and you can have arbitrary number of wires coming off of it. What it's worth noting, corners are not junctions. And in general, we refer to each wire coming off a junction as a branch of the circuit. Just a little bit of vocabulary to help as we're talking about these things. Now, the junction rule says that the total amount of current going into a junction has to equal the amount of current coming out of a junction. So, for example, here, if I had I1 going in, and then I2 and I3 coming out, the junction rule says I1 has to equal I2 plus I3. If I have more than one current going in, so say, for example, like this, I add up all of the ones going in. In that case, it is I1 and I3, and that has to be equal to the total amount of current coming out, I2 plus I4. This is a statement of conservation of charge. The total amount of charge in a circuit doesn't change. It just moves around. So what the junction rule is really saying is that our circuits aren't leaky. All of the current in them stays in them. And we're going to see that we can use that to great effect to help solve for unknowns in our various circuits. Now, the strategy for all Kirchhoff's rule problems, so that is to say all advanced circuit analysis problems, is we use the junction rule to name independent currents in each branch. Then we use the loop rule to help determine them. And depending on what we know and what we don't know, we might be solving for different variables. Sometimes we might be solving for current. Sometimes we might be solving for resistance. Sometimes we might be solving for voltage. But we're always using the same basic algorithm, which is to write down multiple equations using the junction rule and the loop rule and getting that system of equations solved. So let's do a couple of quick examples. We're going to have, I think, 3 things here. This is going to be an example of the junction rule. This is a Kirchhoff's rule, like collection problem, like that does all of it. But we're not going, I'm just going to briefly talk about this one. Then we'll do this one out in detail, and that will lead us to the quiz for the day. So we'll see how much of this we can get through. If we don't get through it all, take a look at your notes because they work, everything's worked out there before you try the lecture quiz today. All right. I'm going to go through this one pretty quick because it's a relatively straightforward application of the junction rule. But note what I do, just for like bookkeeping, is I want that to be red. Is the first thing I do is I just label each junction with a node. This is not like a technical thing. I'm just saying I put a dot at each place where 3 or more wires come together, just so I have a visual idea of where the junctions are. And it is often helpful to label them. So for example, this might be junction 1, junction 2, junction 3, junction 4, junction 5, junction 6. There are no right or wrong answers here. There are no right or wrong answers here because this is just labeling for your own reference. But I just like to label it with J and a number if I have more than one. There's a question in the chat. Is the difficulty of exam 2 the same as exam 1, or was it changed as well? Broadly, the intended difficulty remains the same. The average on exam 1 was sky high as far as this class is concerned. I do suspect a not insubstantial amount of that was due to some academic integrity violations that I'm following up on. So the difficulty, sort of unscaled, like if I try to remove the cheating aspect of it, was a little less than 70, which is in keeping with what we expect from exam 1 in this course. As a result, we did not change any of the difficulty on the exam, or at least the basic difficulty. But what I will say, in general, is that students in this class generally tend to find the Unit 2 content easier than the Unit 1 content, and so I expect the average will be slightly higher, even though we're building it at the same intended difficulty. Of course, individual mileage may vary. Some students might be much more comfortable with Unit 1, or might be comfortable with neither. Hard to say for sure, but in general, I would not expect any differences as far as the sort of design philosophy of the exam is concerned. The end result was ultimately a sort of fair distribution along the lines of what we would typically expect in this course. I hope that answers your question. Once you've labeled all of the junctions, then it is just a matter of writing down the current in equal to the current out for each of them. So for example, for junction 1 here, I1 is going in, and I2 and I5 are going out. So I1 is 9 amps. That's going to be equal to 4 amps plus I5. And note, I can solve this right away to determine I5 is, in fact, 5 amps. I could do the same thing for J2. Now this is 5 amps. And maybe what I'll do is I'll do my loops, or rather my junctions here in blue, just to keep it visually a little bit neater. Here, I've got I5 going in, I3 and I6 going out. So 5 equals 1 plus I6. I6 then clearly equals 4 amps. I can do J3, 4 amps in, I7 and I8 out. Note that I don't have enough information to solve this one yet. There's a question in the chat, how can you tell if the current is going in or out? It's literally just the direction of the arrow. So if the arrow is pointing towards the junction, it's going in. If the arrow is pointing away from the junction, it's going out. Same way if I gave you, for example, a doorway, and I told you somebody was walking in this direction, they would be going into the doorway. And if they were going that way, they were walking out of the doorway. Same idea. In this particular case, we can't solve this because we don't know I7 or I8. So we got to leave that one for later. We'll come up to J4. Here I've got 1 amp going in, I7 going in, and I4 going out. So that's 1 plus I7. That's, I don't know what that number is. I7 equals 3. That tells me I7 is equal to 2, which means I can come back down to that equation I couldn't solve before, plug that in, which gives me I8 equals 2. And I can continue this process throughout the rest. Let's see, J5 is 4 amps in plus 3 amps in equals I9 out. So I9 is equal to 7. And then we do this last check down here of I8. I8 is going in, so that is 2 plus I9, which is 7, which if I had one coming out here, that would give me 9. And sure enough, the current coming out of here is the same one that's coming out of the battery, which is, in fact, 9 amps. There's a question in the chat. To build the system of equations, we analyze each junction and note them. That is broadly correct. In this particular case, we didn't actually require a system of equations. We could mostly just solve each one of these as one step. But what we'll find is when we go to problems that involve both loops and junctions, that will no longer be the case. Now, this problem is labeled in a certain way, and I encourage you to go through the version in the notes just to understand what's being displayed on this slide. What I would like to do instead, though, is I would like to analyze this version, which is unannotated, so I can do the whole thing start to finish from scratch so you can follow along and really see what I'm doing in each one of these cases. Now, what I'm going to do is I'm going to do 3 different colors here. I'm going to do red, blue, and green. I'm going to use red for annotating the various things in the circuit. I'm going to use blue to label loops, and then I'm going to do, green to label junctions. And the first step in all of these is always label everything. Specifically, branch currents. Well, let me say it this way. Currents, 1 for each branch. Then polarities for all devices. So when I say a branch, what I mean is I want to go from a junction to another junction. And the wire between those 2 points represents a single branch. I want to label a current for each one of these branches because we're trying to think of it as currents being things that terminate at junctions. They go in and then different currents come out. This is not indicating like that something is actually changing. It is just saying that the total amount of current is changing in each one of these branches. So here I've labeled one of my branches as that up-down wire between junctions A and B. And I have a battery. I know currents generally come out of batteries. So I'm going to label that I2. And I'm going to label it I2 even though it was the first one I did just for reasons that will become clear momentarily. Remember, it doesn't matter if you guess the direction right or wrong. Just label a current direction that seems intuitive to you and then stick with it. Never change it from there. If you do that, then the problem will work out. Now, the next branch, which I'm actually going to label the first branch, also goes from A to B, but it goes along this path here. This is also going to have a current in it, and it's also reasonable to suggest that it's going to come out of the battery. And I'm going to call that I1. Note that I1 exists everywhere in that wire I have currently labeled blue. There is one more branch here. That's this one. Oop. Try that one more time. That's this one, and I got to label a current there as well. Generally, it's just a safe bet to label the currents as coming out of the battery, and I'm going to label that I3. Okay, so I have labeled all of my currents, one for each of the 3 branches in this circuit. Now I have to label the polarities. So remember that the battery polarities are easy. They always just have the long side as positive, the short side as negative, so those are just fixed. But the resistor polarities depend on the direction that the current is going. Now, I1 exists in this branch. So it's going to come out of B, go up through the battery, and come back to A. So since it's coming this way, it goes in to the resistor on this side, indicating that this side is the higher voltage, and it comes out at a lower voltage. It then gains some voltage across the battery, and then it goes in, high, out, low. I do the same thing for this second branch. I2 goes from B to A. That's up. So it comes in on the high side, goes out on the low side. One last step here. I3 comes out and around like this. So it comes up, out, goes through the battery, in on the high, out on the low. And now I've completely labeled my circuit. But I'm not done yet, not done with labeling. We want to identify independent loops. Independent loops are just closed paths through the circuit. So, for example, let's say I start at A. This is a closed loop that starts at A and ends at A. And that is a perfectly reasonable loop to label. So I'm going to go ahead and do that. But remember that when we're doing loops, they not only have to be closed, but you also indicate the direction that you're going around them. Now, loops are not physical things necessarily. These are just paths that we're going to take to add up voltage changes. So if I were to go in this direction around the loop or this direction, it really doesn't matter. I'm going to choose to go clockwise just because, literally no reason other than I've just decided to do that. And I'm just going to label that loop 1. This little arrow, this little curly arrow, is just there to remind me that I'm going around this interior loop in the clockwise direction when I am doing my loop rule. So then I want to identify an independent loop. Now I'm going to briefly use a different color here, even though my loops are going to be showing up as blue, just to illustrate a point here. So here's another obvious choice for a loop. It's that closed green box there. And I'm just going to, again, choose the same direction. I'm going to call that loop 2 because, fine, yep, that's great. Now, the reason I know this loop is independent is because it includes new circuit elements that were not in my original loop. This loop, L1, included the 2-volt battery, the two 1-ohm resistors, the 2-ohm resistor, and the 4-volt battery. Note that these 3 elements, this 1-ohm, and this 4-volt battery, these are not in my first loop, so this green loop here is adding new information. What do I mean by that? Well, there is in fact a third loop that you could label in this circuit. It's the red loop that I'm drawing now that goes around the entire perimeter of the circuit. However, note that every circuit element in the red loop is already part of either the blue or the green one. As a result, this red loop is not going to give me new information. Therefore, this is not an independent loop. In fact, in general, if I have, for independent loops, if I have n loops, usually something like n minus 1 will be independent. So here I had 3 loops, but only 2 of them give me new information. Third and finally, identify independent junctions. That is, again, usually n minus 1. For example, here is what I'm going to call junction A. Down here is what I'm going to call junction B. Turns out those are both going to give us the same equation, and we'll see that here in a second. So I only really need one of them. The final step, write down a number of independent equations equal to the number of unknown variables. If I have 3 unknowns, I need 3 equations to solve for them. If I have 12 unknowns, I need 12 equations to solve for them. And so you just want to make sure the equations you're writing down are independent per what we described above. Now, in this particular case, this is asking us for the currents, I1, I2, and I3. So we need 3 independent equations to write those down. Now, those equations are going to be the 2 independent loop rules, L1 and L2, and one of the 2 junction rules. I do my actual, maybe I'll have better luck if I write this down on the other side. I do my loop rules the same as I did before. I choose a spot. Let's say, for example, I start at A, and I'm going around this way, and I just apply my voltage differences. Starting here, I go down through the battery. That's positive to negative. That is a decrease. So I lose 4 volts. I come down, negative to positive. That is a gain of 2 times I2. Note that the current I multiply my resistance by when I'm doing Ohm's law is whatever current is in that branch. For this resistor, it's I2, but as I continue my loop around and I get to this one, going from positive to negative, so that is a drop of 1 times its current. The current here is the one in this branch, which is I1. I then come around and I gain 2 volts. I drop 1 times I1, and then I'm back to where I started, and I get 0. So I'm just going to clean this up a little bit. The positive 2 combines with the negative 4 to give me negative 2 volts. I get plus 2I2, and then note I have 2 factors of I1 minus 2I1. That's going to equal to 0. And actually here right away I can already do something to simplify this. I can divide through by 2, and I get minus 1 volt plus I2 minus, I'm going to drop the units because it's a little bit confusing. Dividing through by 2, I get 1 plus I2 minus I1 equals 0. But note that I can't solve this yet because I have 2 unknowns here. I'll then write down my second loop rule. So that's this one. I started at A last time, so how about I start at B? And I'm just going to follow my loop around. So I'm going to come up, positive to negative. That is a loss of 2 times I2. I gain 4. I'm running out of room here, so I'm going to have to do this in a couple lines. Then I gain 1 times I. That should be easier to distinguish from an I. 1 times I3. Then I lose 4 volts. Then I gain 1 times I3. And that's going to add up to 0. Here, note the 4's cancel out. I get negative 2I2 plus 2I3 equals 0. Again, I can divide through by 2 to get this result. One more step here, and then we are basically finished. It's just to write down a junction rule. Okie dokie, we can do that. We got to pick one, A or B, doesn't matter. We'll choose A. And note that this might seem a little confusing. I1 comes up and goes in, I2 goes in, and I3 comes up and goes in. All three currents appear to be going in to my junction. Now, many of you will come across problems that are like this, and you'll feel the need to correct yourself. Like, this can't be right. I can't have all of my current going into one place. I gotta change something. Don't. Yes, this means that we labeled the direction of one of our currents incorrectly. But remember, that is okay. All it means is that one of our currents is going to end up with a negative number. And that will tell us which one we labeled incorrectly. So don't change anything. Write down the current in, which in this case is I1 plus I2 plus I3, and set that equal to the current out, which in this case is nothing. That's fine. Now we have three equations. 1, 2, 3. And you can solve these in any way that you like. Systems of equations, you can do substitution, yada yada. You have so many options. So what we're going to do here is we're going to solve this to say that I2 must be equal to I3. We're going to then, let's see, plug that where? We're going to plug that in here. That will tell us I1 plus 2I2 equals 0, which tells us that I2 is negative 1/2 of I1. Sorry, I'm in the way. And then we're going to take this result and plug it into our equation up here, which gives us that negative 1 minus 1/2 I1 minus I1 equals 0. Rearranging this slightly, I get, let's see, negative 3/2 I1 equals 1, or I1 equals negative 2/3. That means I2 is going to be equal to positive 2/6. And that means I3 is also going to be positive 2/6 amps. Now, of course, I want to make sure that I didn't make any silly math errors, so I'm going to go into the notes here real quick and double check that I didn't make any algebraic mistakes. Sorry if my microphone's being a little wonky. But the end result of this process is that we have a number for each one of our currents. Yep, 2/3. And, well, yes, of course, it is worth noting that 2/6 is, of course, 1/3 amps. So note that the fact that I1 came out as negative indicates that I1 is the one that I labeled incorrectly. And this should make sense. I have two big 4-volt batteries pushing current this way, which is going to overpower the tiny 2-volt battery here. So yes, I1 is actually going to be in the other direction, but that's fine. I labeled it as going up. Here it's negative, so that just really means it's going down. Notice I didn't have to change anything about my diagram. All right, that was a long-winded example, but the notes include more. It works through this example in its entirety. It works through this example in its entirety, which will prepare you for this example, which is the quiz for the day. Take a look at the notes and make sure you're well prepared for this. Something I am going to note for you is that this is an open circuit, meaning this is these are not connected to anything. That means these wires here do not have current flowing through them. Current only flows through the central loop here. In general, current only flows through closed circuits. This is the Kirchhoff's analysis. This will appear on the exam, so I suggest that you actually look ahead to homework 7, specifically problems 4 through 8. Those are going to test your ability to apply Kirchhoff's laws to different scenarios. And again, make sure you go through each of the other worked out examples in the lecture notes. With that said, folks, have a great day. I will see you on Wednesday. Let me know if there's anything I can do. I was unfortunately tied up at the hospital most of the weekend, so I have plenty of emails that I need to get back to. And so if you're waiting on a response from me, I apologize. I'll try to get back to you today. Set up an office hours appointment if you have any immediate questions. Otherwise, I'll see you Wednesday for the last lecture of Unit 2. Just to remind you, this is your quiz. Pause the video here if you would like to do it now. Otherwise, take a look at your notes, and I will see you, I don't know, Wednesday. What day is it? Oh, there's a question. Is there lab today? That's going to depend entirely on your individual classes. I think the answer is yes. I'm double checking the syllabus right now. Lab schedule is the 19th, 20th, and 21st. Yes, there are labs this week. You're going to be covering Ohm's law. Then it looks like next week there is no lab again, as they allow us to catch up with the lecture. After that, the next 2 weeks are a little bit funky because we have Election Day and Veterans Day in back-to-back weeks, so that's going to change the schedule around a little bit, after which point it should be more or less smooth sailing for the remainder of the semester. So yes, you should be getting information about your lab schedule from your lab TAs, but my understanding is that yes, there are labs today. Have a good one, folks. We'll see you Wednesday.